Hardware to Save a Planet explores the technical innovations that are giving us hope in the fight against climate change. Each episode focuses on a specific climate challenge and explores an emerging physical technology solution with the person bringing it into reality. I'm your host, Dylan Garrett. Hardware to Save a Planet is brought to you by Synapse. Make sure to click subscribe so you don't miss any future episodes. Thanks for listening. Hi, everyone. This is just a quick note to say that we're trying something a little different with this episode. It was such a rich conversation that we've decided to release it in two parts, with part one being today and the second part coming in the next episode. Hope you enjoy it. Hello and welcome to Hardware to Save a Planet. I'm here with Casey Handmer, the founder of Terraform Industries. Terraform's goal is to make cheap natural gas from sunlight and air. I love this because I have so many conversations about curing the world of our hydrocarbon dependency, which just feels like this incredibly daunting challenge. But Casey's approach is to continue enabling us to use gas for energy, and he has a way for us to do it sustainably. The basic idea, as I understand it, is that as solar energy gets cheaper and cheaper, it becomes more and more cost-effective to use solar electricity to power direct air capture, to pull CO2 out of the atmosphere, to power electrolyzers, to generate green hydrogen from water, and then to use methanation to combine that hydrogen and the carbon to produce methane or CH4. Casey has been extremely thorough and quantitative in designing his approach to this business and has detailed his thinking in a white paper available on the Terraform website, which I would highly recommend reading. I'll say the overwhelming impression I get is that his level of intellectual curiosity and productivity are through the roof. He did his PhD at Caltech in theoretical and mathematical physics. He has spent time as a space scientist and system architect at NASA and a levitation engineer at Hyperloop One, working on high-speed ground transit. He's also written 2 books about the challenges and solutions to colonize Mars. And among many other things, he spends time flying planes and arranging a cappella music. Casey, it's really an honor to have you. Thanks a lot for joining.
Well, thank you for having me here and look forward to the conversation.
So from what I can tell, you've spent a lot of your life exploring the idea of space travel with a specific focus on Mars. I'm curious, I meet a lot of people working on climate in various ways who have spent parts of their career in the space industry. Why is space travel important to you, and how, if at all, does it relate to the work you're doing at Terraform?
Yeah, that's a great question. Space travel is something that many people find inspiring, increasingly wary of post hoc attempts at rationalization for things that you're just intrinsically interested in. And I've been interested in space for as long as I can remember. I'm not all that surprised to find that both the space industry and the climate tech industry are infested with the same kinds of people, because I think that for both of them, the raw importance of technology as a mechanism to solve problems is so undeniable that you sort of find the people who like to think of problem solving in terms of technology development, engineering, and so on will be attracted into those spaces. And then I think a lot of people, especially recently, have really acquired incredible skills in the space industry and have always had a ideological commitment to doing something about climate or energy. And so when they're ready to take a quick break, maybe from getting rockets into space or robots onto other planets or something, they want to try something that's a little bit more close to home. Often energy and climate is the next port of call.
And for you, do you see them as wholly kind of different and independent efforts, or do you see space travel as kind of our ultimate solution to the damage we might do on this planet?
No. The mere idea that like space is some kind of escape hatch is ludicrous on the face of it. Even an Earth ravaged by like thermonuclear war would be significantly more hospitable than even the most hospitable parts of space after lots of effort. It's not even close. Yeah, there'd be parts of the world where you wouldn't even be aware that the nuclear war had occurred, most likely. And it takes quite a lot of imagination to imagine kind of like when that would not be the case. I think they are linked, however, and kind of within a broader overall platform or vision for a future for humanity where we continue to put in generationally appropriate levels of effort to emancipate our kind of evolutionarily compromised biological heritage from the otherwise undeniable and unavoidable realities of starvation and poverty and fear and death, which we've been able to do a reasonably good job of so far with technology. And I think that if you want to paint a vision of like continuous human improvement forever, as opposed to, well, we've improved everyone's standard of living by a factor of 100 since before the Industrial Revolution, that seems like a natural place to stop, then space travel is necessarily a part of that story. And then obviously, if you are doing space travel in any kind of serious way, you need to be thinking about setting up energy productivity in space locations, so on other planets or on asteroids or in deep space. And it turns out that many of the same constraints that apply there also apply here. So it's kind of a very rich vein of interrogation or investigation to try and understand kind of, how humans will live and thrive on Earth in, say, 10,000 years, in much the same way they may live and thrive on giant space stations in 10,000 years.
It's clear you've thought about these things a lot and kind of the future of humanity. Is that kind of thinking how Terraform came about? Were you specifically looking for a way to address climate change specific, or what was the kind of origin of the idea behind Terraform?
Yeah, I've always been deeply concerned by humans' environmental impact and climate change in particular. But many, many years ago, kind of graduated from, wouldn't it be great if we all just blah, 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 to people actually pretty reliably do what their incentive structure causes them to do, to then understanding like the sheer necessity of copious, available, cheap energy for continuing to pursue and execute on kind of various socially valuable or humanistic goals. So in particular, nothing really moved the needle on global poverty until we made oil cheap. And then it was easy. And this is becoming increasingly obvious that that energy is by far the most important fundamental factor of production for economic progress. And countries that have secured supply chain to cheap energy basically do just fine regardless of governance quality. Almost all of them are success stories, even though the governance is mixed at best. And whereas countries that have failed to secure supply of cheap energy are often in severe economic distress, regardless of the quality of their governance. Even with excellent or what is considered excellent governance, if they don't solve that fundamental strategic imperative to keep energy prices low, then their primary and secondary industries flee, and then they have no basis upon which to build and rebuild wealth for their current citizens, let alone their future citizens. I think it's really important to kind of understand that. So I think in the context of kind of the space problem, I've been thinking about this for a very long time. At the same time, I'd also been kind of embarking on this project to try and understand as much as I could about how humans would ultimately do all the same sort of stuff on Mars. And then these projects converged in a number of ways. And so while my initial motivation with Terraform was to find a scalable business model that would allow me to ramp up carbon capture, what does a business model that is able to create a huge amount of value around captured carbon look like? I very quickly realized that actually, any system that solves climate change or solves carbon emissions will be doing it as a side effect of another more important business, because people in general just don't, like, their revealed preferences, they don't care that much about the price of the carbon that they're emitting, and they're not really willing to pay all that much to avoid it. Plenty of people will be happy to like post on Facebook or something like, oh, I turned my lights off today. But when it actually comes to how they feel and how they vote with respect to fuel prices at the pump or whatever, the evidence is extremely strong that people, for obvious reasons, care deeply about cheap energy prices. And kind of part of this exploration was figuring out how this works on Mars and how we get hydrocarbon products on Mars. And obviously a Mars base like a nuclear submarine would be largely electrified. But there are some chemical processes and some applications where you really need a lot of hydrocarbon fuel. And in particular, if you want to come back to Earth from Mars, you're going to need a lot of fuel to do that. And eventually realize that like these processes are mostly, like, almost entirely just about energy cost, right? And if you can solve cheap energy, you can solve the process, and if you can't, you can't. And then remaining curious about progress of solar power, which I kind of have seen for more than a decade now as kind of the great hope for us doing something about climate change here on Earth and energy abundance. Noticed that it had become cheap enough that it was kind of in the ballpark of how cheap it would have to be to do conversion of ambient water and air into fuel. But obviously, like within the ballpark, and then actually like verifying that it is close and actually converging, and then actually building an organization around making that happen. Kind of three extremely different things in terms of like the level of insight required to do it. Now, by 2019, I thought, well, this is pretty obvious. This is going to happen. Why is no one else working on it? And after a year or two, I realized actually this weekend is the 3rd anniversary of incorporating Terraform. I kind of realized, well, maybe it's really obvious to me, but it has to be, if it's just barely obvious enough to me that I would prepare to like quit my job and actually try and build this thing, right? Which is a very high threshold, kind of binding energy to overcome. Maybe other people think it's like obvious, but it's not worth their effort, or they're not the right people to do it, or just unaware of it. And I would say in retrospect that, a lot of stuff that seemed obvious to me back then is now more obvious to people today, but it's still not obvious in general. Like it's still not, blindingly obvious in say the way that, and actually even this is still fairly niche, but like progress in AI, for example, has become much more obvious in the last few years, even though if you were paying attention, you would have noticed the early signs of it maybe a decade ago. Yeah, so that's kind of the origin story. It's very exciting. It's kind of a flash of insight. And then spent about a year doing a bunch of experiments, just trying to get smart on these issues. And in particular, people have built synthetic fuel systems in the past that are capable of producing fuel at enormous cost. But if you want to take advantage of solar getting cheap, you need to be able to build the synthetic fuel system cheap, so you can pass on the cost savings to your customers, and that's how you'd set up the business. And it was not immediately apparent to me, and I think it is still very unapparent to most other people, that it is possible to build synthetic fuel plant for kind of cheap car money as opposed to cheap private jet money. It makes a really big difference as far as the scalability of the business model goes, though.
I definitely want to get into how you solve that problem of making it so cheap. First, I'm curious if you could help just explain, what is it about hydrocarbons? Maybe this seems like a simple question, but why is this the ticket? Why are we so dependent on hydrocarbons specifically, and to what extent is it about sort of our whole infrastructure and society has evolved based on them? So we are where we are now, and is it that there's something fundamentally about this as an energy source versus other potential energy sources?
I think the success of hydrocarbons, like many things, is overdetermined. So it happens that the hydrocarbons we use as fuel are also just objectively excellent fuels. It also helps that they are pretty abundant on the earth, compared to other potential fuels. Humans burned wood for fuel for tens of thousands of years, but as soon as the Industrial Revolution kicked off in Britain, they basically exhausted their wood supply in a few decades, which was a major problem because they also depended on wood as a building material for the ships that they needed to, Britain kind of uncontested control of global waterways throughout almost a century, actually. And so they needed to find additional sources of fuel, and they began with coal and then moved to oil, and now we're kind of moving more to gas for a variety of reasons. It is certainly true that roughly a third of the US economy is electrified, or energy economy is electrified, something between a quarter and a third in terms of like net energy usage. And it is also true that the trend is towards electrification. So we're seeing a greater adoption of electric heating and cooling, rather than burning coal, bunker oil for heat in winter or something. We are seeing a greater adoption of electric power for ground vehicles, so cars, some trucks, some trains. Electrification of trains obviously is not new technology, but it's not a widely adopted technology in many countries. And obviously like a substantial growth in demand for energy applications for computing. But at the same time, I think people who think that it is possible for us to completely electrify our civilization, it's an extremely tough road to do that. That there are a handful of places on Earth where it's extremely hard to get hydrocarbon fuels for a variety of reasons, and they've done their best to electrify to avoid that. And it's been extremely mixed success. Like these are generally not places that you would regard as having a high standard of living. They're still very dependent on oil imports for a variety of reasons. So hydrocarbons are typically used as fuels. So when we think of hydrocarbons, we think of natural gas. I think of propane. Think of acetylene for welding torches. Think butane for your lighter, gasoline and kerosene, jet fuel, rocket fuel, you name it. These chemicals are also used a lot in synthesis. So for making fertilizers, for example, for making plastics, paints, pigments, medicines, et cetera, et cetera. So, a huge fraction of our hydrocarbon consumption is actually going into kind of embodied products, including plastics. So one of the things I like to say is like look around and point out the things that that involved hydrocarbons in their production, and the answer is like everything, right? Because mostly everything is covered with a layer of paint, which is derived from hydrocarbons, or like pigments in your clothes or whatever. So they're absolutely essential. And I think I can't give much credence to people who say that, oh, if we just stopped using oil, all our problems would go away. Because they are correct in one sense, which is that if we just stopped using oil, something like 3/4 of the world's population would starve to death in less than a year. But I don't think that's quite the same as saying all our problems go away. I know, like, finally instituting full communism does not solve that. That might accelerate the starvation somewhat, but the outcome is the same. So basically, it's unavoidable. It's unavoidable. You absolutely have to have a hydrocarbon supply chain, and I think that it is particularly for high energy applications. So we're talking long distance shipping, aviation. What a wonderful thing aviation is. Isn't it amazing that we can fly around the world in a day instead of having to spend 8 weeks on a dangerous ship? How valuable is that time? And then obviously rockets require fuel as well, although relatively small amount in the grand scheme of things. And so I think that it is reasonable to expect that while demand for, say, gasoline is probably unlikely to grow rapidly because of the explosive growth of electric vehicles, particularly in growing markets, at the same time, I would not expect demand for gasoline or natural gas to collapse anytime soon. I think its growth rate has slowed, but it's still an awful lot. It's still like 50 gigatons of CO2 a year. And then you have to ask yourself, well, what's around the corner? The answer is, if you want more energy, you have to make more energy, right? And the crazy thing is with solar panels, at least, you don't even need all that many of them, right? Like most of Europe's surface is devoted to agriculture, so row crops, grazing, and forestry, all of which are solar powered, right? All of which is basically extremely inefficient and extremely environmentally destructive. We think of it as like a natural kind of bucolic rural environment, so nothing like the kind of 8,000 years ago environment in Europe, which was largely forested environment, monoculture crops and so on, compared to solar panels, and it's about 1,000 times lower economic productivity. So like if you just forked over like 1% of the least productive agricultural land in the entire continent to solar power, you would like double the energy wealth of the continent overnight, which is nuts. And I'm really surprised that I've not seen this happen.
Yeah, it's interesting because if that's true, I mean, that like capitalism should, those forces should be driving that to happen, right?
Yeah. So, I mean, the outcome with solar is not in doubt. So last year we deployed about 440 gigawatts of solar worldwide, which is slightly less than 1 megawatt per minute, which is pretty remarkable if you think about it. A megawatt is, a few acres of solar. And in the last 9 months, China deployed 160 gigawatts just by themselves. When you think of like paragons of good governance and personal freedom, you don't normally think of the Chinese government, but at least they're not getting in the way of their own citizens having enough wealth to be able to like afford to reproduce, or to be able to afford to live somewhere, or to be able to afford to not freeze to death in winter. And China's also, obviously extremely aware that they import 12 million barrels of oil a day through sea lanes they cannot control. So, they're serious about it. But Europe's in the same situation. They import actually more than that in terms of oil per day through sea lanes they don't control. If someone can block up the Suez Canal by taking a wrong turn, your energy supply is not safe. So, yeah. So, like, the outcome is not in doubt. Like, I see the same thing in the United States. Like, the effect of kind of this choking regulation is it just slows the process down. But at the end of the day, like, Europe will have its solar power. It just can choose whether it'll be poor by the time it has it or not. That is the question.
So what's your feeling on, because I feel like a common response to this idea that there are these sort of hard to abate sectors, aviation, maritime shipping, heavy industry,
steel, aviation.
A common solution, is hydrogen, right? Or I don't know. It feels like I rarely hear people talking about hydrocarbons being our long-term ticket here. What's your take on all this?
I think all
this energy we're putting towards green hydrogen and things like that. Yeah,
I think people broadly underestimate how difficult hydrogen is to work with and overestimate how hard it is to make hydrocarbons. This I can attribute to basically just failure to update on the cost progress of solar and what it implies for everything. And this is a story I've been banging on about for a while, along with a few other people. But I think that it's a bit like the COVID pandemic. It's an exponential, and people don't really understand how to comprehend where they are in that process. If hydrogen was such a compelling fuel, why is it that the hydrogen industry is composed mostly of companies that raise money and then go out of business? If hydrogen was such a compelling fuel, why has no one ever used it preferentially to power anything? So basically, you've got this spectrum of like applications for chemical energy by like the energy intensity required. And hydrogen has a nice property, which is that its energy its enthalpy of combustion per kilogram is quite a bit higher than other gases or other fuels. Although once you roll in the cost of the oxidizer you need, and you roll in the cost of the storage and all that kind of extra stuff, it's much more of a wash. But generally speaking, you think of hydrogen as having advantages for extremely high energy applications. So you can look across the spectrum of energy applications, from like running your lawnmower to like driving a car, operating a train, running a ship, running a plane, running a rocket, and say, where on this spectrum is hydrogen currently dominant, and which way is it going? Right? And the answer is hydrogen is not dominant at any point in this spectrum. Right? Hydrogen has arguably a handful of applications with a handful of rockets that are in the process of going out of business. I think that there is a great future for hydrogen applications in chemistry, but it's as an intermediate product. Right? It's not as something that you try and store and transport and use at the consumer end. You produce it and then you consume it straight away. So for making fertilizer, making steel, potentially via DRI, for making hydrocarbons, you make the hydrogen and then you consume it like 10 seconds later. And I actually do think that hydrogen is the best lifting gas for airships, but it's some regulatory barriers to using that right now, unfortunately. But I think it can be made safe for using for airships, and that its benefits certainly has benefits. But actually, it's kind of interesting. It's usually the same people who say that hydrogen is the best fuel ever, and we should obviously use it to power cars that like random people drive around on the road. And at the same time, it's much too dangerous for airships. And you're like, well, pick one or the other. Right? Like if it's way too dangerous for airships because of all the stuff we know about, like hydrogen embrittlement and much higher flame speed and DDT, I was like deflagration, detonation, transition, and leakage, and a bunch of other nasty properties that hydrogen has, then
why put it on the road?
It's not impossible to make a safe hydrogen car. It is impossible to make a safe hydrogen car that has good value, right? And that's just, that's kind of a rather long extended rant about that. But I have a running list where I've basically been keeping track of various hydrogen projects that I've heard about and what's been going on with them, and it's not looking good, right? There's a huge shakeout occurring here, and I was at a conference a few years ago where someone, I won't say which company they were from, stood up at a Q&A with some representatives of the Biden administration, and they said, look, the $3 per kilogram production tax credit under the Section 45E of the Inflation Reduction Act is a good start. But if the Biden administration is serious about kickstarting the hydrogen economy, it's going to have to be at least $6. And I looked at this person, and I looked at my colleague who was there with me, and I looked at this person, and I couldn't believe my eyes, because in some ways, 45E was kind of an error in some ways. Like the fact that it's $3 is already seen as like anomalously generous in comparison to the other subsidies that are present in that act, many of which I think are slightly better calibrated. And like it helps us, and I'll take it. Don't get me wrong. But the idea that like, oh well, hydrogen is a commodity that sells for $1 a kilogram, and even with a $3 subsidy on top of that, we can't make this work. And actually, if you dive into the weeds on most green hydrogen producers, they're talking more like $8 on a good day and $15 on a more reasonable day per kilogram of green hydrogen, which is just kind of where the cost ends up if you do it the old school way. And they somehow think that this is going to be a compelling hydrogen product. There was a fabulous podcast recently with Mike Leibrich and I can't remember her name, but some representative of the German Hydrogen Alliance or something like that. And apparently, like at least by their account, the approach that Germany is taking to the fact that their industry is like literally dying from energy starvation and does not want to adopt hydrogen as a alternative fuel to natural gas because it's like 10 times the price, is that they're just going to force them to do it. And how well do you think that's going to go? How well do you think it's going to go to like force their actions, force them to buy the gas, force them to internalize that cost and then pass it on to their consumers? How do you think that will help Germany's competitiveness on the world stage? Right, quite aside from like the safety costs and so on. At the same time that like at Leuna, which is actually the plant where they first developed the Haber-Bosch process and then the Burgess and the Fischer-Tropsch process for making liquid fuels out of coal, they're trying to stand up a hydrogen fueling type situation, and their hydrogen transport truck blew up like a month ago. This is not moving in the right direction. It's kind of how mean do I want to be here? It's a bit of a race to see like whose delusions about the nature of reality and how much it likes hydrogen versus how much it likes nuclear fission power is going to win out. I think that there's a possibility that fission will find a bit of a niche, but hydrogen as a standalone fuel it's DOA. It always has been. And like Elon Musk has gone on record about this. And like, do you really want to bet against that guy? He recognized in 2008 that the Tesla Roadster that they shipped in 2008, which used the best lithium-ion, well, not even the best lithium-ion batteries, but like good lithium-ion batteries for that era, which is almost 20 years ago, was achieving better performance in terms of value for money for its customers with that car that was like losing money at an incredible rate than than hydrogen fuel cells could at that time if they achieved their theoretical maximum efficiency, which at that time and even today has never been achieved even in a lab. In the last 20 years, it has not gotten better for hydrogen. It has gotten much worse. Batteries are like, 20 times cheaper than they were back then. Like, I don't understand why we keep having this conversation. It's ludicrous.
All right. Well, I think, yeah, we've effectively put that to bed, I think. But
any other things you'd like me to be mean about? I'm ready.
This is great. We could do this all day. It's a good transition probably to what you are specifically doing, because you are doing what you said in terms of producing green hydrogen and using it on the spot, as I understand it. So I was wondering if you could just kind of walk through the major steps of your process, the actual terraformer, I think, as you call the product. What are the major components?
Yeah, the terraformer. It's a good question. So the fundamental important thing to do is to generate a product that people want to buy, and not just indifferent to, but desperate for. And so if you produce a fuel that is backwards compatible at a good price, then people will buy it. So, there's advantages and disadvantages to commodity products, but the advantage is that there's not really any market risk. The disadvantage is that, often the margins are pretty slim and there's a lot of competition. So we want to make natural gas. Natural gas is the easiest hydrocarbon to make by far. So it's the natural beachhead product for us. We can actually get substantially better profit margin from making liquid fuels from methanol, but it's harder to make. So you start with natural gas. We need a source of CO2. We need a source of hydrogen. We get the CO2 by direct air capture. We have some, tricks and tips over there, but I'm going to focus on hydrogen for right now. In order to make natural gas at a sensible price, you have to be able to make hydrogen for on the order of $1 per kilogram. The commodity price, right? So actually right now, if you want to get hydrogen via steam methane reformation from natural gas, it's about $1.50. That's kind of the price that ends up going into fertilizers and stuff like that, maybe a bit less than that. But these are huge processes in very large plants. They're fully amortized. So the fundamental question you have to ask yourself in this business is, do I have a hope of being able to produce hydrogen for on the order of $1 or not? And if I don't, then I should pack up and go home, because I can make fuel. Anyone can make fuel, but no one wants to buy gasoline for $100 a gallon. It's just not a good deal. So what does it take to produce hydrogen for $1 a kilogram? And you start to look at a big pie chart of all the different things that contribute costs to your hydrogen cost. And actually, conventionally, the electricity cost has been a large number. We're talking $5 or $6 overall. But as a fraction of the overall hydrogen cost, it's relatively small. So if you're talking green hydrogen for $15 a kilo, and maybe electricity is $4 or $5 for that, then it's obviously you're screwed on both fronts. So you have to kind of look into why it's costing that much. And so first of all, you need super cheap energy, right? If you're buying electricity out of the grid, you're not going to make it. It doesn't matter if your electrolyzer is 100% efficient, you're going to be losing money. So you have to go off grid to some extremely cheap source of energy. And in our case, solar is the cheapest energy ever. That places additional constraints on you, because if you're using cheap solar, you on average only have about 25% utilization of that solar resource, because
the sun doesn't shine all
nighttime.
Or 24 hours. Yeah,
that's exactly right. So you have to have an electrolyzer which is able to make money at even 25% utilization, which means that not only are the conventional ones too expensive, they're actually four times even more too expensive than you thought. But you also have to be able to turn them on and turn them off like a light switch, which is considered to be quite challenging with conventional electrolyzer designs for a variety of reasons. Okay, so we've solved the cheap energy part. We're going to take cheap solar straight out of the panels and plug it straight in somehow. And solar is getting cheaper over time. And so if we're able to build the electrolyzer cheap enough, then the cost of the power will be 50 to 60 or 70% of the overall cost of the hydrogen. As that power cost comes down, we'll capture that upside, pass it on to our customers. Everyone's happy. Okay, how cheap does our electrolyzer have to be in order to make that work? And it's on the order of $100 a kilowatt. It's actually we're targeting quite a bit less than that, but $100 a kilowatt's about right. So what does that mean? Well, a kilowatt is roughly as much power as you can take out of a wall socket or an outlet in the United States. So if you think of appliances that you plug in that have thick electrical cords, right? So things that are taking up lots of power, a food processor or a microwave or a hairdryer, electric kettle, something like that. They're typically drawing about a kilowatt. How much do they cost? And electric kettle's about $15. Microwave might be $150. A nice food processor is probably about $100. So it's kind of in that general range. Generally the range of inexpensive, high-powered desktop, kitchen appliances. So it's not physically impossible to build things that can be operated safely, that that perform transformations matter, like an electric kettle boils water, for that price point. Okay, how much do conventional electrolyzers cost? It's about $2,500 a kilowatt, right? So that's like starting to edge into like consumer computer territory kind of thing, right? So like your computer won't consume that much power, but it costs about that much money, maybe even more. So like it's a different level. You say, well, that's a lot of money. It's quite clear if I'm paying $2,500 a kilowatt, no matter how efficient it is, no matter how good my utilization is, I'm just not going to make money. I'm not going to be able to get down around $1 per kilo. So you start to look at all the different reasons why they cost so much. And the reason is because the default assumption is you're running off grid power, which is too expensive. You're getting absolutely killed on your OpEx. You need to maximize efficiency. You say, well, take a conventional, cheapest chips, alkaline water electrolyzer like the one we're building here, and you want higher efficiency. Well, put it under pressure, have a flow-through system, have special catalytic coatings on the electrode plates, run it at higher temperature, do a bunch of other kind of things to it, and pretty soon you've got a device that is about as engineered as a nuclear reactor. So if you look at the system overall, you take the electricity at the cheapest possible price we can get it, which is a solar array. It's literally an inert pane of glass, sits on the ground and converts sunlight, which is free, into electricity, which is the highest grade form of energy that we have. Then you take that power out of the array and you put it straight into the electrolyzer. So you have no intermediate transportation costs for the electricity, no grid transportation, no transformers, no power conversion, no nothing. Put it into the electrolyzer. The electrolyzer is super cheap, and it's not super efficient, but it doesn't matter because it's really, really cheap. And it makes hydrogen. And then the hydrogen is also really expensive to store and transport. So don't store and transport it. Just move it through a tube, to the next component in line, which is the methanation reactor. And the methanation reactor takes that hydrogen and converts it into methane, which almost immediately transforms it from a dangerous and not particularly valuable commodity because of handling difficulties into a much less dangerous and much more valuable commodity, which is natural gas. And then you also need a source of CO2 locally because CO2 is also expensive and annoying to transport. So you also have to do CO2 production locally. And so all in all, you end up kind of with this very interesting set of constraints, which is I need to build a small modular chemical plant that can operate in the field autonomously and can operate intermittently. And if you can solve those really interesting technical challenges, then you have a machine that performs this kind of real-time arbitrage between different forms of energy, like sunlight at one end and hydrocarbons at the other, which is able to perform this really dramatic kind of transformation and value generation. So roughly speaking, per acre of land, our system is about 100 times more productive than bioethanol. So if you're just growing plants to make them into fuel, versus using solar arrays, which do not require irrigation, sowing, pesticides, fertilizers, et cetera, it's actually far lower environmental impact to put solar panels on the ground than to plant, to plow and plant. And you get about 100 times higher value out of it. And I think if we make on the order of 100 million of our terraformers, then we'll be doubling the energy output of the world and very quickly displacing drilling as the preferred way of getting energy, which is super, super valuable. I think it's massively underrated. And again, it's 2024, and I'm surprised that so few people are really taking this seriously and really trying hard to make this work.
Hey, this is Dylan again from the future, jumping back in quickly to remind you to check out our next episode when it drops in a couple of weeks to finish the conversation with Casey. Hardware to Save a Planet is brought to you by Synapse. To find out more about us and how we develop hardware solutions for the world's most ambitious companies, head to synapse.com. And then make sure to search for Hardware to Save a Planet in Apple Podcasts, Spotify, and Google Podcasts, or anywhere you like to listen. Make sure to click subscribe so you don't miss any future episodes. On behalf of the team here at Synapse, thanks for listening.